perfect cloudless day, you would get, and that would probably be not in depth of winter, but more like in spring, you should get 1.36 kilowatts out of a 100% efficient solar cell. So it's a whole lot of energy from the sun. Okay, sunspots. We'll see those before too long. There's still sunspots occurring, but they're pretty small. This is what the more energetic periods look like with these large sunspots that you can actually see with the naked eye. But what they are is regions of very strong magnetic fields. And they're actually cooler than the rest of the surface of the sun. The only thing important to remember is that they are magnetic. And they're very, very strong. Sunspot numbers, they've been measured for hundreds of years. It's a really kind of an archaic method, but they retain that method because there are hundreds of years of data recorded. So they continue to use that method so that the data we record now is traceable back to the data that was collected ever since the early 1800s. And they've actually gone back and corrected some of the data in the 1800s to use it more consistently the way they should have done if they had computers back in 1830. I won't go through the details, but this is how that's done. If anybody wants to do that, you can see it on the internet or by looking at these slides. The lowest possible sunspot number is 0. That's when there are no visible spots on the sun. And higher sunspot numbers tend to have much more solar activity of all kinds, not just sunspots. And the highest sunspot number during the period that we've been recording it for several hundred years occurred in 1957. That's kind of a legendary year. If anybody talks to old-time hands like me, 1957 is their year. But I remind people, what would you rather have? 1957, sunspot number of 190, and maybe a DX35 transmitter and an SX100 receiver. Or would you rather have today, with an Electron K3 or a Yaesu FTDX5000 or your favorite radio, I think we're better off now, rather than going back to that SX100 receiver. I prepared this presentation about 3 months ago, and we were going down this slope and steadily going down, and about 2020 is when we expect the actual minimum to occur. And we're heading that way pretty fast. This is one way to record sunspot numbers, or actually individual sunspots. You notice what they've done here is they've plotted the latitude of the sunspot versus time. And this answers one of the questions about how do you know it's a new sunspot. This is the beginning of the sunspot cycle, when sunspots tend to occur at high latitudes, both north and south. And as the sunspot cycle matures, the sunspots become closer and closer and closer to the solar equator. So this is the beginning of a cycle, this is the end. And if you look here at the end of this cycle, notice there are new sunspots from the next cycle occurring at high latitudes, while the old sunspots from the last cycle are fading away at low latitude. So this is just a plot of individual sunspots over 130 years, and it follows this cycle. And there's 1957 right there. See how much? These are strong, there are more sunspots and they're at higher latitudes. And this is only over a 4-year period of the previous sunspot cycle. This was kind of the peak of activity, and there were all these sunspots in the summer of 2000. And only 4 years later, the only sunspots were at very low latitudes, and there were just a couple of them. That's kind of where we are now. Just a few sunspots, and they're at very low latitudes, kind of down here. So let's look back over 400 years. People have probably heard this term called wander minimum. It's kind of the, oh no, the end of HF propagation. Well, the good news is, I don't think any, and you'll see this in a slide coming up, I don't think any of the solar scientists today think this is going to happen in our lifetime, thankfully. But you'll see another trend. A couple of other things. those of us who've been licensed for the last anywhere from 10 to 50 years have been lucky to live through this period that's often called the modern maximum. It started in 1947 and ran through about 2002, when the sunspot cycles were unusually strong. And you can see in this chart how unusually strong these are compared to the early 1900s when radio was just getting going. And the last deep minimum occurred, HF radio was discovered in about 1921. So the last minimum, which we're about to enter, occurred before long-distance HF radio existed.
How do they know that occurred that far back if we weren't?
Well, scientists have been counting sunspots for many, many years. I always found it interesting that the first scientists that started counting sunspots were in London. Has anybody ever been to London? You ever see the sky?
Well, it's probably the only place you can do it and not go blind.
Far back then. Why did he do it back then? Oh, I think just curiosity among people, I think scientists just started noticing these things on the wanted to know about it. And they figured out ways to go back and look at trees and other things, even back before 1600.
I remember.
Figure out these. It was about the same time. Yeah, the telescope was about the same time. Yeah. And the telescope was invented primarily so they could get a more accurate way to determine time.
Perfect for that. Nice and big.
Okay, so there was a lot of money involved in getting very accurate time back in the 17th century. Because if you knew very accurate time, when you were on the high seas, you could avoid hitting land. You could use maps. But if you didn't know the time, you couldn't figure out your longitude, and you'd get into a shipwreck. So there was big money in trying to develop very accurate ways to determine time, and it turned out telescopes were, that's another story, telescopes were key to that. Okay, anybody see a trend here? Yeah. Anybody notice a trend? So here we are, right here. Here we are here. So this is the sunspot cycle we just went through. This is the one up before. This is a pretty strong one in 1990. And this is the next one. Where should I put my finger?
It's very lower.
Down here?
No,
A little higher? Well, most of the scientists think it's going to be about like the last one, up around here, up around 100. So still pretty weak, but not the one minimum. But nobody knows for sure.
Is it going down because the sun's burning out?
Nobody knows what's actually happening. Scientists are trying to figure out the detailed workings of the sun. But I mean, you think about it, the sun is billions of years old. We've been observing it for a couple hundred years. We've only had real good instruments for about 10 years. So that's not much of an observation period. Let's say a 8 billion year old star. So what they actually do, kind of interesting, is they're starting to study other stars, because it turns out that our sun is not the only star that has sunspots. Lots of other stars have sunspots too, and they're at different periods in their age. So they're looking at other stars to figure out what might happen to our sun and what happens over time. So anyway, yeah, probably minimum in maybe 3 years, and back up here to about where we were in about maybe 2025. So we get to enjoy 160 meters for a while. So this goes back and looks at the last 2 cycles. And of interest here is this last cycle had 2 peaks. Very common, by the way. Very common for cycles that have 2 peaks. Because what actually happens is the northern hemisphere of the sun, sunspots don't occur on exactly the same schedule as the sunspots on the bottom half of the sun. So what's actually happening here is the northern hemisphere of the sun had its peak here, and then about 14 months later, the southern hemisphere of the sun had its peak and it was stronger. And there was a pretty disappointing quiet period in between where we were worried, oh my God, we started down this ramp already, and then all hell started breaking off on the sun, and we enjoyed it for a couple of years.
Out of curiosity, can you comment about the mini ice age? Some people say that it may be linked to this.
It might be, but that's not the topic of this presentation. If I go off on that hint, we might not come back.
But do people have a mini ice age?
I don't know. So look that up on the internet, you'll get lots of interesting opinions, most of which are probably wrong. Okay, so let's look at some of the stuff. Let's look at some of the stuff that comes off the sun. Again, this is a relatively quiet sun, but it's not quiet at all. And this is during one of the solar peaks when there's lots of sunspot activity. And you notice there's some in the northern hemisphere up here, and there's some in the southern hemisphere. And again, here in this photograph, there was one sunspot cycle, and it's almost on the solar equator. And that all happened in just a 3-year period.
What are those actually images of? Magnetic activity or?
These are, I don't know in detail what was happening in that month in 1999, but these are probably solar flares and individual sunspots as well. And there's coronal holes here. These dark areas are cool areas. These are coronal holes. There's a coronal hole here in this quiet period.
We get the radiation also from the coronal hole.
Yeah, well, it turns out the coronal hole is an area where all kinds of particles can escape from the sun.
Okay.
I think what he's asking, is that in the visible spectrum, or is that in certain energy?
It's in all kinds of spectrum.
Oh, it's a broad.
It's a broad spectrum, and I don't know what the spectrum of this was, but you can see that it's different. I don't know what this, but scientists image the sun in all kinds of different wavelengths, and they see different objects at different parts of the spectrum, not necessarily the visible spectrum. And then there's this thing called the solar wind. And the solar wind is particles. It's not electromagnetic, so it's traveling more slowly, and it carries heavy objects, ions, electrons, and neutrons. It takes about 3 or 4 days to get from the sun's flux. The solar wind has kind of a background level of particles that are just routinely falling from the sun, and then during particularly active periods, the sun boils off more ions, electrons, and neutrons than it normally does, and it sends them to Earth very rapidly. And the amount is billions of tons per second. It's a pretty minor amount of explosive material from the sun, equivalent to probably 100,000 Hiroshima atomic bombs continuously. So it's during quiet periods, the solar wind doesn't bother the Earth very much, and I'll show you a diagram that shows that. And during more energetic times, it can cause blackouts. And this is taken during an eclipse, and you can see solar flare activity. So the sun is behind the moon in this photograph.
It makes sense.
So this is kind of what the solar wind looks like. It travels in, sorry, this is the Earth. This is the Earth. So what's happening here is the solar wind is coming towards the Earth here, and the Earth's magnetic field deflects a lot of the activity away from the Earth. And then there's a tail of the magnetic field of the Earth on the dark side. You notice on the sunlit side, so the sun's over here. On the solar side, the magnetic field of the Earth is compressed by the solar wind, and on the night side, it gets pushed way out from the Earth. And this is one of these coronal mass ejections, a CME, and compare the size of the ejection of billions of tons of solar material to the Earth. Is the Earth. And there's one of these coronal mass ejections. And here's what it looks like compared to the sun. And it's right on the limb. So this would be directed away from the Earth, not towards the Earth. So it's all about magnetic activity on the sun. These are tangles of magnetic activity that cause these sunspots to occur and eruptions to happen. And they happen all through the sunspot cycle, but it's a lot more complex and energetic during periods of high solar activity. These are coronal holes. And so when you hear about a coronal hole, if you had a telescope that could safely look at the sun, it's these dark areas here. So these are low density regions that allow mostly X-rays to escape the sun. And if these X-rays hit the Earth, it causes problems with HF propagation. And these coronal holes can happen throughout the solar cycle, even at the bottom. But they're more common and more energetic at the top of the cycle. And the solar wind mostly originates from coronal holes. So there's a video of solar flares.
That will ionize the ionosphere?
Well, the ionosphere is mostly ionized by ultraviolet light.
Okay.
And the most energetic ultraviolet light occurs from sunspots. So this stuff is mostly the stuff we don't want to see.
Oh.
This is what causes geomagnetic storms. And I'll describe that in a little bit. So these were taken from spacecraft, just massive, and you can see what happens is when it escapes the sun, it blows up and all that material gets directed throughout space. The Earth is this tiny little dot, but some of it hits us, but the vast majority misses the Earth. Only the tiniest amount hits the Earth.
What's the time frame on the picture on the left?
Well, you can see it here, so it looks like it's about 4 hours. Yeah, about 4 hours.
Okay.
Like that. I'm not sure if that's hours or minutes. I honestly don't know.
Okay.
Could be minutes, yeah. But it's at least 5 minutes, and it could be several hours. I suspect it's minutes. So it starts at 08 and runs through 11. So that might be 4 or 5 minutes, and I think that's kind of what it is.
Minutes from the
Yeah.
right hand.
Okay. So solar flares are this extremely hot gas, and the nasty thing about that is it contains something called energetic protons. They have a tremendous amount of energy. And if they get pulled into the Earth's atmosphere, it causes terrible things, and I'll show you that in a little bit. Solar flares also carry very large amounts of X-ray radiation, and that appears at the Earth in only 8 minutes, very fast. It's very rare in this part of the sunspot cycle, but at the top of the sunspot cycle, there are things, some people call them radio blackouts, where all the bands go completely dead. The scientific name is an ionospheric disturbance, sudden ionospheric disturbance, SRD. A lot of hands call them radio blackouts. Has anybody experienced one of those?
Oh, yeah.
Tell me what your experience was.
It was March 1989. I had to go out to the grocery store to get something. I left my radio on. I was on 30-meter band, and at that time BBC was still on. It was blasting in. I come back 10 minutes later, and like everything was dead. I go around. I pulled a handprint of another sound key, and I asked him, he told me yes, I did. It was like 15 minutes.
Yep.
And it lasted for hours.
Yeah, and so your experience is just like mine. They happen suddenly.
Yeah.
And they last 2 or 3 hours. When the bands come back to the way they were, gradually, it happens suddenly, like somebody flipped a
I
switch.
got something wrong with my antenna.
Yep. A lot of people try to debug their radios. But they happen suddenly, and after 3 or 4 hours, the bands are just like they were before it happened. But then 2 or 3 days later, you get the energetic particles and everything goes down. And it stays pretty bad for a few days. So that's a solar flare. Sun ionospheric disturbances can only happen in the daytime. Right. Where we live on the Earth has to be able to see the sun, otherwise it wouldn't affect us. So if anybody ever tells you they experience an SID at night, they're wrong. Can't happen. But in the daytime it does. There are all kinds of different flares. The most energetic ones are called X flares. We're not going to see any of those anymore, but the scientists can classify them in all kinds of different ways. The weaker ones are going to continue. X flares we're probably not going to see anymore, but I can only say probably. Coronal mass ejections, this is when billions of tons per second of energetic particles are launched from the sun. And they're still happening at this part of the sunspot cycle. And we happen to be in the place where they hit the Earth, causes really bad effects on propagation. Here's a video showing a CME, all that material, billions of tons leaving the sun. And there's a little timer on it too. I can't quite see it. And all of this material is magnetically charged.
Will particles eventually reach Earth and become part of Earth?
Yes, some of them will become part of our atmosphere.
Okay.
But the vast majority won't. Remember, compared to the sun, compared to all of the space around the sun, the Earth is a pinprick. You get all this space. So the vast majority of this stuff never gets to the Earth. And most of it that gets to the Earth gets pushed away. I'll show you that. So here's a little detail about the size of space weather storms. That refers to solar flares and CMEs. This is a good time to describe this. So all of these materials coming from the sun have magnetic fields, powerful magnetic fields associated with it. It comes from a plasma on the sun. And the Earth's so here's the Earth here. The Earth's magnetic field is northward pointing. If the interplanetary magnetic field, the magnetic field associated with all the stuff coming from the sun, does anybody remember from elementary school experiments with magnets? Remember that? So if magnets if you put the north pole of the magnet against the north pole of the other magnet, you couldn't push them together, right?
You had the two skies.
But if you turned it the other way, they hit. So this is showing what happens when these magnetic particles and X-rays from the sun are of the opposite magnetic polarity of the Earth. And what happens is it gets sucked into the high latitudes of the sun and cause things like auroras. If the planetary magnetic field is the other way, remember those magnets from elementary school, the Earth is able to push all that stuff away. It gets pushed away from the Earth and never gets in. So the polarity of the interplanetary magnetic field is a big deal. The ham radio guys don't like to see it this way because that means the bands are going to be dead. The guys that like to watch auroras love it because it means the sky is going to be bright red. So I just said all that stuff about the orientation of the interplanetary magnetic field. So how does all this stuff affect Earth? Well, first of all, the sun rotates at about 27 days. The sun is a gas star, it's plasma, it's not solid. So at the equator, the rotation of the sun is about once every 25 days, so it's turning faster. About 25 days later, the same observables will repeat. Way up at the polar regions, it takes about 35 days. And this differential speed is one of the things that causes all this stuff to get all tangled up on the sun.
Because it's not solid.
Not solid. And it's turning it, it's rotating at different speeds and it's getting all tangled and twisted.
That's really true.
So, but for most of the sunspots occur in this region here. So the rotation for the areas where sunspots are, where we really care, tends to be about 27 days, more or less. But if somebody says, no, you're wrong, it's 25 days, well, of course they're right, near the equator. Or no, it's 35, yeah, of course they're right, near the pole. And remember, the Earth is tilted a lot. So there are huge seasonal effects. Although the sun, there's no such thing as a seasonal effect on the sun. On the Earth, it makes a big difference because we all know that we're in the winter now, so we're facing away from the sun. We don't get as much energy. But isn't it kind of odd? Remember I said early in this presentation that the best time of the year for propagation on the higher HF bands, 15, 12, and 10 meters, is during the fall and winter, when we in the northern hemisphere are pointing away from the sun. So we're getting less energy, right? So why are the high bands better when we're getting less energy? That seems kind of wrong. But it's true. There's a lot of complicated reasons for that. But there's one reason that's easy to remember. Suppose we went back to elementary school and ran some simple experiments we used to run as kids. They could get a balloon, fill it with air, and then hold it above the stove, the heat source. What happens to that balloon?
Expands.
Expand, exactly. And that's exactly what happens in the summer, in the northern hemisphere, and the reason the higher bands are not as good. What matters for HF propagation is how many electrons there are per unit volume in the ionosphere. So you want high electron density. But what happens in the summer is that the ionosphere gets overheated when we're facing the sun. So instead of all these electrons being in a compact place like they are in the winter, because the ionosphere is cold, so we have high electron density in the winter because the ionosphere is cold. In the summer, we've got more, but the ionosphere expands because it's hot. Yes?
But doesn't when you increase the amount of, in parallel with this, when you increase the amount of magnetic activity from the sun, doesn't it also take more energy to broadcast anything? Because there's independent motion of the particles already, and it takes more energy to alter them.
There's kind of two major things going on. One is ultraviolet radiation. That's just the normal light, but it's not light, it's ultraviolet, so it's higher frequency. And that's coming from the sun all the time, and that's electromagnetic radiation. It's light. Regular light is electromagnetic too. And that's just always radiating from the sun, and it's more intense when there are more sunspots. The other stuff which you're referring to are all of these particles that are exploding from the sun. And that's what causes all of these problems with propagation, all the absorption and all that. And yeah, it's billions of tons per second, but compared to the size of the sun, it's totally insignificant. The sun has been radiating countless hundreds of billions of tons per second of particles for billions of years, and it's hardly made any difference at all. So it just doesn't matter because the sun is such a massive. But for us who are interested in HF radio and the effects on the ionosphere on the Earth, it makes a big difference.
What about if you're closer to the equator? Is there much of a difference between day and night?
The answer is yes. And the ionosphere behaves a whole lot different than the equator. I've operated in South America, so you're pretty close to the equator there. I guess we were in Venezuela, so it's a little bit north. And the bands are open later at night. They open early in the morning. But there are also some unusual phenomena in the ionosphere that cause a lot of signals that are coming off the ionosphere to sound kind of warbled. And some of there's a lot more absorption because there's so much more. Down near the equator, you're pointed almost at the sun for much of the year. And it gets such intense solar radiation that some of the absorption that happens, and I'll mention the D layer, is much more intense. So the bands, instead of kind of gradually opening and gradually closing, they kind of suddenly open. And then they suddenly close because of the way the absorption happens.
There's something the engineering team at the Equatorial missionary broadcaster, HCJB,
yeah.
used to talk about the Geo effect. The combination
Yeah, they're right on the
on the equator and up in the mountains as well.
Yeah.
Could I just clarify here? The basic mechanism though, when the atmosphere becomes ionized, it becomes more metallized, right? It's like a metal,
Not really a metal.
which supposedly bends the radio waves because the E field is affected.
Okay, so let me give you another idea to think about.
Okay.
The atoms that are being ionized, and what ionization is, it's tremendous energy from ultraviolet light that strips electrons from mostly oxygen atoms. And the thing that's important for radio, we hear about ionization, but the ionization is atoms of oxygen that have had electrons stripped off. And the oxygen atoms have no effect on radio waves. They're too heavy. They can't move fast enough to react to the very rapid high-frequency oscillations from radio. But the electrons that have been stripped off of those oxygen particles can react very fast. So what's happening is, we don't care about the ionization. What we care about is the electrons that got stripped off. So what we care about is electron density. And what that does is when electromagnetic waves get into the ionosphere, it slows them down and causes them to refract. So reflection is really the wrong term. It causes the radio waves to bend as they pass through this area of high electron density. So,
But that refraction effect is due to the electron motion, right? I mean, it's
yes,
affecting
the electrons,
wave field of the electric field of
it's
the
electromagnetic field, exactly right. There's another fascinating thing that happens. It's a plasma, this thing, the atmosphere full of these free electrons is a plasma. And when a radio signal, an HF radio signal, enters the ionosphere, it splits into two parts. And one of those split parts, they're called E and O waves. One travels high in the ionosphere and one travels lower in the ionosphere. Then they recombine when they come back out of the ionosphere and come to the ground. And that is one of the things that causes fading. Listen to shortwave, particularly these days of AM, you could hear the signals fading up and down, and that's the interaction of those two parts. It's also interactions with other things. But anyway, it's electrons that are actually being disturbed by the radio waves going through, and it causes them to bend. Yes?
And then when the sun sets, those electrons go back.
But not entirely.
Strip, and they go back?
Yes.
Okay.
But not completely, otherwise the bands would go totally dead.
Okay.
So what happens is, as we approach sunset and then go through the night, there are fewer and fewer of these free electrons for exactly the reason you described. They recombine with these ionized oxygen atoms. But they don't all recombine. So the electron density goes down, but it doesn't go to zero. So as the night goes on, 15 meters closes, 20 meters closes, 30 meters closes, 40 meters stays open, 80 meters opens up. It's been dead all day long.
That's great.
Well, gray line is still another thing, and I'll show that too.
Okay.
It's related. It's what happens on the gray line is the electron density. The gray line is the boundary between daylight and darkness, and I'll show you that. And along the so-called gray line, some people call it the terminator, electron density tends to be constant along that line. So you get propagation that can carry yourself more than halfway around the world by following this area of relatively constant electron density at the border between daytime and nighttime as you go around the world. And I'll show you a map of that in a little bit. Okay, so I kind of showed this before when some of these particles are coming from the sun, and ideally, if it's like the magnets in elementary school that are oriented the same way, those particles get pushed away from the Earth. But when it's oriented the other way, they get sucked in, and we have things like aurora and dead ambience and that kind of thing that happens. So we've already talked about these three different types of space weather storms. Sudden ionospheric disturbances, those are solar flares that occur in our daytime when we're looking at the sun. Then there are solar flares and coronal mass ejections, which are these unbelievably massive clouds of particles. Tens or hundreds of billions of tons per second. So again, we've kind of talked about this already, where ideally all of this stuff gets deflected around the Earth if the orientation of the magnetic field of these particles is the same as the Earth. So if this is north pointing. But if it flips the other way, then a lot of this, not all of it by any means, but a lot of it leaks into the Earth at high latitudes and causes, see right here, aurora. Right at this boundary right here, where all these particles get sucked into the Earth. And this is an image of the sun during a period of very high solar activity. And we've already talked about a lot of this already. So what happens if the storm on the sun at t = 0, think about timing like a rocket launch. So at t = 0, a flare or a solar or a CME occurs. 8 minutes later, the X-rays, the electromagnetic stuff, and the ultraviolet light emitted there arrives at the Earth only 8 minutes later. And then 30 minutes to 40 hours later, depending on how heavy the particles are, all this highly magnetized stuff appears at the Earth. And then after 4 days, propagation tends to return to normal as this stuff fades away and we go back to background level. We've already talked about SIDs, I won't get into that. What it does is strongly ionizes the D layer, which causes dramatically increased absorption. That's what causes the SID to cause all the signal to go away. It's very heavy ionization of the D layer. And it takes about an hour, maybe more, for everything to return to normal. And here's the aurora. We don't see has anybody ever seen the aurora in this area? Anybody seen it? You have, okay. I haven't seen the aurora in this area in about 20 years, because you have to be lucky. It has to be light without any clouds, and you have to kind of be away from city lights. But I saw an absolutely spectacular display about 5 years after we built our house. And it was one of these displays where it looks like curtains hanging from the sun sky. And it looks otherworldly because these curtains appear to move at thousands of miles an hour. You see the curtains hanging in this part of the sky, and a moment later, bang, they moved over to this part of the sky, and they're moving the whole time. It's just incredible. Now, this is a routine thing to see. If you go to Fairbanks, Alaska, or Iceland, or way up like in Bergen, Norway, when you're at high latitudes, but around here, it's unusual. And for it to happen around here, you have to have very intense, usually a CME will cause the aurora to drop way down to our latitudes. But if you get up into northern Windland, you'll see them much more often, or in southern Canada. And if you go to Fairbanks, Alaska, you see them all the time. Which is why many of the solar scientists live in Fairbanks, Alaska. Okay, briefly looking at the ionosphere. So now we're getting away from the sun. And you've probably heard about these things called the F layer. And in the daytime, it splits into two layers called the F1 and the F2. For those of us who like to work DX, it's the F2 layer we really care about. It's the highest refracting area. It's about 250 miles over our head. And the F2 layer is a daytime only. And at night it becomes the F layer. And then there is the E layer that primarily causes sporadic E propagation. That's the thing that causes 6 meters and even 2 meters. Even 432 megs sometimes. Rare. To open up where you can work long distances on those bands, mostly in June and July. And then that absorbing layer, the D layer, no signals get refracted from the D layer, but they do get absorbed, especially during SIDs. And here's another look at the relative heights of things. Meteorites that you may have seen from time to time, shooting stars they call it, a little bit lower altitude than the D layer. Sounding rockets and that kind of thing are kind of at the level of the aurora. And then the space shuttle flies at about the same altitude as the F layer. So there's the D layer, it's at about 80 kilometers. And it's an absorbing layer. It happens every day during the day. That's what causes 80 meters to go completely dead during the daytime, except for local propagation. And it happens every day, just normal. And during SIDs, that absorption that affects 80 meters extends all the way up to 10 meters. And then the D layer totally disappears after sunset, allowing you to work DX stations anywhere in the world on 80 and 160 during the night, when that band is useless during the day. And E layer is higher. It's densely ionized during the day. That's what causes 40 meters to be a good daytime band for working around the eastern part of the United States. That propagation is off E layer. And it's real good on 40 and 30 meters. During field day, when we can operate 40 meters all day long, that's what we're using is the E layer. That's not sporadic. It's not sporadic at all. It's very predictable. 40 is open for 400, 600, 800 mile propagation every day, all the time, very reliable. But that's the reason you don't hear DX on 40 meters during the day. The radio signals can't penetrate the E layer to get up to the F layer during the daytime. So you won't hear signals from England at 1 o'clock in the afternoon on 40. But as the E layer starts to get weaker and weaker as the sun goes down, and the F layer comes back, and we can work all over Europe late in the afternoon and during the night. And sporadic, that's the kind of propagation that we experience on the VHF bands in June and July. And sporadic is the right word. You can't predict when that's going to happen. It happens. It might be here today, and you tell your buddy about it, and you listen to the band tomorrow, and it's dead. And he calls you on the phone and says, "What are you talking about? This band is dead." Well, yeah, it was yesterday. But it's sporadic propagation, so it might not happen again for 2 or 3 hours or 2 or 3 days. No. But it's exciting. And you can work, believe it or not, you can work around the world on 6 meters with this sporadic heat propagation. It isn't limited to just working 500 miles. The most distant QSO I had on 6 meters was on Christmas night, 2015, when I worked 6 stations in New Zealand, 6 meters. New Zealand, that's almost halfway around the world.
Now, why do you believe that was E rather than F2 propagation?
Because it was a combination of things. First of all, nobody knows exactly what it was. It lasted for about 2 hours. On the New Zealand end, you could only work stations in that city where all these earthquakes occurred recently, in Christchurch. If you were within 50 miles of Christchurch, we could work them.
Okay.
But if you went within 50 miles of Christchurch, it was a narrow propagation. It might have been something like a duck. And that's characteristic of sporadic heat. So in the southern hemisphere, Christmas is summertime down there. So summertime in Christchurch, you don't have any Christmas lights there because it doesn't get dark. And it was sporadic heat down there. Up here in the northern hemisphere, we were in our weak E season. So E propagation occurs in December, but it was unusual because in the northern hemisphere, people were working New Zealand that night all the way from Maine to Missouri. So it wasn't focused on the northern hemisphere. So exactly what it was, who knows?
Is it possible it was a combination, a couple hops of E and then an F hop? I mean, does anyone ever go to study that?
Nobody knows. But it was certainly unusual, because usually it's focused. And it was very focused down in Christchurch. But on the East Coast, it was literally named in Missouri. Incredible. Fun to think about, but nobody knows the answer. So here's the F layer. That's the layer we use. We were over at the radio club tonight listening to the W3T. And we were getting all frustrated because he was only working Europeans. Couldn't hear this little vertical on the roof of the building over there. So they were working F layer, very reliable propagation here, making us frustrated in New Jersey. And that's probably, it was late afternoon, probably simple double hop F layer from Washington DC to Europe. And we were relying on kind of a weak E layer fading away fast, signal getting weaker and weaker as we listened to them working Europeans and not us in New Jersey. Okay, so we can get a little more of this on. So these are kind of the same points I made before. During the daytime, the DE, F1, and F2 layers are ionized during the day. At night, right at sunset, the D layer vanishes, which allows 80 and 160 meters to open. And then the E layer, MF, MUF, drops rapidly after sunset, which also helps 160, 80, and 80 meters and eliminates the short distance propagation like from New Jersey to Washington, D.C. at about sunset.
That's that maximum usable frequency?
Yeah, maximum usable frequency.
Okay, thanks.
Can you cover on 10 meters specifically what day and night behavior would be?
Yeah, let's not talk so much about this part of the sunspot cycle,
Just generally.
because at this part of the sunspot cycle, we're mostly limited to being able to work north-south. So at this part of the sunspot cycle, we can work on 10 meters. We can work into South America almost every afternoon on 10 meters. But you're not going to work any Europeans for a long time, because there isn't enough free electrons in the ionosphere for us to work east-west. But north-south it works. There's enough electron density near the equator to support that north-south propagation. But during the sunspot maximum, like we had just until a couple of years ago, we could work the world on 10 meters, mostly daytime. The band opening started a little bit after sunrise. Typically, it started to open to South America first, and then Africa, and then Europe.
What layer?
It would be the F2 layer. And then as sunset approached, the propagation switched from Europe over to the Pacific, where it was much more daylight over on the Pacific side. And then usually about 2 hours after sunset, the band closed.
So it's following the sunlight?
Following the sun, exactly, yeah. And more accurately, following electron density, right? So these are some of the, and this uses the term ionization, but remember, it would be more accurate for me to say in this slide that electron density varies with time of day, season, geomagnetic storms, and the sunspot cycle. But it turns out ionization and electron density track each other. The more ionization there is, the more electrons have been stripped off those atoms, so the more free electrons there are.
Did you say oxygen?
Yeah, oxygen. Okay, so we've already talked about a lot of this stuff. So I don't think we need to cover. Well, here's one concept we didn't mention before, lowest usable frequency. We talked about maximum usable frequency. Lowest usable frequency is usually a result of D layer absorption. So it's usually, so during the daytime, D layer is real active, so the lowest usable frequency for long distance propagation is down around 40 meters. And you can't work anything on 80. And then at night, that, especially in the winter, that LUF drops down below 160 meters. So we could work all over the world on a good night on 160 meters.
Talk about NDIS.
NVIS, that's a different kind of propagation. We use it on field day all the time. Anybody operates field day is using NVIS on 40 meters, for example. So NVIS relies on propagation that goes up essentially vertical. So for those of us that chase the X, we're interested in low angle propagation that gets out to this refracting layer that's 250 miles high. So we want to refract off that layer and get over to Europe or Africa or Asia. But for NVIS, we're interested in very reliable local communications. We want signals not to go way out to the horizon, we want them to go overhead. So what we care about is another concept called critical frequency. And critical frequency is the frequency at which signals that are propagated straight up do not go out into space, but instead are reflected back down. It turns out during the daytime, the critical frequency where signals come up or back down is up to about 10 megahertz. So you can work true NVIS, very close range propagation, up to about 30 meters during the daytime. At night, the NVIS propagation, especially at the bottom of the sunspot cycle, you better have something on 160 meters.
What does that stand for?
Near vertical. Ionosphere. What's the answer?
Near vertical.
Skywave, yeah. Skywave. Skywave is any propagation that goes up to the ionosphere, as opposed to ground. So daytime up to about 30 meters. So 40 and 30 meters are really good NVIS bands during the day. 80 is terrible because of the delay absorption. At night, electron density goes way down, so the critical frequency drops way below 10 megahertz. In the summer and the fall, you work 80 meters NVIS at night, but at this part of the sunspot cycle, you better have something for 160. But you can't work the guy in the next state on Skywave on 80 meters because it's too close.
Talking about ground wave?
Okay, so ground wave is totally unrelated to anything we've discussed. Totally unrelated, because it doesn't rely on the ionosphere. It relies on two kinds of propagation. If you're down near the AM broadcast band, the actual name of that is called surface wave, where the wavelengths are long enough that the propagation actually hugs the Earth as it moves along. And if anybody, most people don't listen to AM radio. Does anybody listen to AM radio? Oh, a few people do. Have you ever driven to a beach on the ocean? And what happens? You can hear signals in the wind during the day, and that's the surface wave coming across the ocean where it's not attenuated very much. So if you drive to Ocean City or Atlantic City in New Jersey, and with an AM radio in your car, you can listen to broadcast stations in New England at high noon. Drive 3 or 4 miles inland and they go on. So that's surface wave.
We used to listen to winds coming through the Straits of Gibraltar.
Yeah. Probably not in the daytime.
No.
At night, yeah. The other kind of so-called ground wave occurs on 80 meters and above. And that is actually electromagnetic radiation directly from one antenna to another and not hugging the Earth. Wavelengths are short enough, and that mostly just depends upon line of sight. So it's true line of sight propagation, direct from one antenna to another, not having much to do with the Earth. But distance does matter, because eventually the curvature of the Earth gets to you, and then one antenna can't see the other. And the actual distance that ground wave works on, true ground wave, 80 meters and above, is about 1.5 times the visual horizon. But then you say, Frank, I can hear people 200 miles away on 80 meters during the daytime. They're weak, but I can still hear them. Well, it's other kinds of skywave and other propagation that's weakly propagated. Okay, so these are some of the measures of the amount of radiation hitting the sun. One is called solar flux. It's been measured for years and years at 10.7 centimeters. Why? You can't, thank God, you can't measure UV radiation on the Earth. Otherwise, we'd all be burned and we wouldn't be here today. So you can't measure UV, ionizing UV radiation on the Earth. It's all been stripped away by all these oxygen atoms that have their electrons pulled away. And by the time the UV radiation would have gotten to the Earth, it's gone. It spent all of its energy stripping electrons. So it doesn't get here. So you can't measure UV radiation on the Earth. But what they discovered is that at this microwave range, that radiation is highly correlated with UV radiation.
About 2.85 gigahertz.
Yeah, something like that. Yeah, it's about right. Yeah. Exactly. Okay, so, and these are two measures of disturbed conditions. K-index, important thing to remember about that is it's updated every 3 hours. So it's near real time. Whereas the A-index is a 24-hour measure of the amount of geomagnetic activity, that means disturbance, for yesterday. Yesterday, not today. So if you hear somebody say, boy, wasn't the A-index high today? Well, we don't know how high it was today because it was measured yesterday. So it's like driving down the Jersey Turnpike with the blinders on the front windshield, looking out the rearview mirror. K-index is the real time.
I'm gonna do that around.
And they correspond with, yeah, I know a lot of the Jersey drivers drive that way. So the high numbers mean bad things for propagation. And A-index is yesterday's numbers. I usually ignore them. So we've already talked about a lot of these topics, so I won't go through that again. There's a couple of things that I do want to. We've already talked about LUF. We've already gone through all that, so we don't need to do that again. This is what happens above the critical frequency. When the NVIS fails, the radio signal actually penetrates the ionosphere and goes out to space. So as the day goes on and the critical frequency goes down, at lower and lower frequencies, the signals don't get refracted by the electron density. They pass right through and head on off to the next galaxy. Okay. We talk about ground wave, 168 meters only, surface wave or space wave, that's somewhat beyond the line of sight. Talk about sky wave, talk about critical frequency already. Here's some of the numbers, so critical frequencies relate to NVIS. Above these frequencies, the signals go out into space. So summer daytime, about 9 megahertz. Winter daytime, much higher, 14 megahertz. Why is that? Because the electron density is greater. Remember the balloon effect over the stove? So you all the way up to 20 meters. You can work NVIS on good days on 20 meters. But almost every day in the winter on 30 meters. And then at night, you better have a good 160 meter antenna, particularly in this part of the sunspot. And because we're interested in things straight up, the antennas don't have to be very high. So our field day antennas work great. Simple horizontally polarized antennas, 20 to 30 feet high, are fantastic. There's another view of what happens when the signals are above the critical frequency and they just go out into space. They get refracted a little bit, but eventually they escape and go into space. And then this is the MUF right here, where the signal goes at the greatest distance, and this is the LUF in here. And then there's this thing called the skip zone, where if you're in that skip zone, you can hear one end of the QSO but not the other. So you can hear if there's a guy in Connecticut working someone in London, you can hear the guy in London, you can't hear the guy in Connecticut. So we talk about that. And I think we talked about that. Surface wave goes to short distance. And there's another thing called backskip, which tends to fill in the skip zone somewhat. Some of the signals that refract off the ionosphere and come back to the Earth, when they hit the Earth, some of them get bounced back towards the transmitter. And you can often, in the skip zone, so in this region here, the skip zone, you can sometimes hear weak signals that are bounced back. And fading is caused by signals that are propagating across the ionosphere in multiple paths. And fading can be fast, as it often is for signals that pass over the Arctic regions. That part of the ionosphere is very unstable. Or very slow, like on 10 meters late in the evening. so I think we talked about sunspot number, is an interesting form of propagation called transequatorial. And I think that was a factor in that QSO that I mentioned between North America and New Zealand. That tends to be F-layer propagation near the equator. So chances are that New Zealand propagation, so here's New Zealand right over here, there's probably E-layer over here that's somehow coupled into this TEP over the Pacific, probably around the Cook Islands here and up around Hawaii here, and then coupled across the United States into maybe a winter E-layer, something like that. So there were at least 3 different kinds of propagation involved in that very rare, very, very rare Maryland to New Zealand contact. And I wasn't the only one. Dozens of people made those contacts. So somebody mentioned gray line, and here's what the map looks like. Yes.
On that previous slide,
Yeah.
something I've always wondered, on the map, that wiggly line in the middle,
This line?
yeah, what is that?
Okay. So if you look closely, it says geomagnetic equator. Something I haven't mentioned yet. So here's what's happening there. Does anybody know roughly where the magnetic pole is on the Earth? Roughly?
Hudson Bay.
Hudson Bay. Yeah, it's north of Hudson Bay, but it's way south of the geographic equator. So this kind of map,
Okay.
the equator kind of runs right across here, right? Through Ecuador, but it's a straight line. But the geomagnetic equator isn't up here, it's way up here, right about there. So for the part of the Earth that's near the equator, near the geomagnetic pole, or the magnetic pole, geo just means Earth. So for the part of the Earth that's near here, the geomagnetic equator is pushed south.
Halfway between the north and south pole?
Well,
The magnetic pole.
between the magnetic, and I don't remember where the south magnetic pole is, but it's somewhere in Antarctica, and it's not near near where you'd expect it to be. So this gets pushed south, and over on the other side of the Earth, the geomagnetic equator, the real equator is over here somewhere. So it gets pushed north. So, and it's very frustrating. These dotted lines show transequatorial propagation, and our buddies in Europe can routinely work transequatorial propagation on 6 meters into the area around South Africa. Works perfect. But the poor guys in North America, our geomagnetic equator is pushed way down south into Brazil. And unless you live in Florida, you can't work TEP. Unless you get lucky. Because that New Zealand Christmas thing was probably TEP. So it was probably some kind of E-layer that got the signal from Maryland over to California, and then it linked across the magnetic equator with TEP here, and then wound up here in Christchurch, New Zealand. Definitely by an E-layer path, as it was focused.
Aren't the poles supposed to be flipping sometime soon? You know, stories I've heard.
Well, sometimes a long time, but I don't think you and I need to worry about that.
Wouldn't the net effect mean no magnetic poles for some
We
period?
don't know. We don't know. I don't think
We'll be long
gone.
gone for that.
I saw a documentary from NASA, on the NASA channel, that the flipping of the poles were actually overdue for it already.
Yeah. But I don't think, we're not talking about human lifetimes here. We're talking about periods of time that are probably measured in thousands and tens of thousands of years,
Yeah,
not
10
human lifetimes.
to 15,000 years.
Yeah, something like that.
But we're already over the time period that it should have flipped.
I wouldn't worry about it, you will.
By any time.
And of course, the last time it flipped, which was probably 10,000 years ago, there's no recorded records, we don't know what happened.
Yes, but will my VHS collection still work?
Okay, so here's the gray line, so we talked about that. So, it's really interesting, for anybody that operates 40 meters, for example, so so this is daylight, and this is darkness. And as the afternoon goes on, this thing called the terminator, or Ham's called the gray line, moves further and further, and here in New Jersey, at this time of year, at about 5:30 in the afternoon, it starts to get dark. And if you can launch a radio wave along this thing that Ham's called the gray line, along this boundary, where do they wind up? Japan. There's a lot of hams in Japan. So it's very easy to work from the United States to Japan by going 3/4 of the way around the Earth by following this daylight-darkness boundary. You can also work into Western Australia. There's not as much ham activity in Western Australia, but there's enough. So that's what gray line is.
Is it better in morning gray line or in afternoon gray line?
Well, it happens at both times. So in our afternoon, so let's just imagine that this whole map slides left about an inch. So in our afternoon in December, January, we can work the gray line 3/4 of the way around the Earth to Japan. Now let's pretend that this is light. I don't have another map. That this is light and this is dark here. Well, the other thing that happens is that well, maybe an easy thing to pretend. Let's pretend that this is the United States over here. So the gray line, instead of being southeast towards Brazil, towards the South Atlantic, in the morning, at sunrise, it's kind of southwest. So you're kind of pointing down over New Zealand. So the gray line propagation at our sunrise kind of allows us to, I wish I had a map showing this, but this area winds up kind of over here, around India and Southeast Asia. So at our sunrise, you can kind of work this same path, point southwest instead of southeast, and the signal winds up in South Asia. So you can work stations in India, Thailand. There's not a lot of hams there, so there's not as much activity. The opening is the same as it is in the afternoon, but it's open to parts of the world where there aren't as many hams.
Does it work the other way too, like northwest is northeast instead of southwest?
Well, the time when this, see, if I had maps of the whole year, you could see it. But most of this 40-meter propagation occurs during our winter. During the summer, the night is very short. So, at this time of year, the night lasts, what, 15 hours maybe? Darkness from 5:30 and, well, let's say December, from 4:30 in the afternoon until 7:30 in the morning. So we've got 15 hours of darkness. But in the summer, these same things are here, but most of the benefit of it is in the southern hemisphere where the nights are long.
My question was, to do that, you point the beam like southeast.
Yeah,
Follow
in
the line.
our afternoon, so at 5 in the
But
afternoon.
if you pointed it northwest, would it do the same thing around the other way?
Yes, but that's, yes, you can also work Japan in that direction.
Like the northern route?
But here's the problem. And this shows, most of that path is in daylight. So, it really only works well on 40 meters at the very dead bottom of the sunspot cycle, when the absorption here is reduced. So for most of the sunspot cycle, in the afternoon on 40 meters, if you want to work Japan, it's 3/4 of the way around the Earth, just in this darkness period here, where the D layer is inactive and the E layer is very weak. But only in the dead bottom of the sunspot cycle, like maybe 2018, will you be able to work this path here, pointing northwest, over to Japan. And the reason is there's too much daylight. So the absorption, even though the path is a lot shorter, there's too much absorption in all this daylight. And the darkness is way up here in this Arctic region where there's all kinds of disturbed propagation.
You're referring to D-layer absorption.
D-layer absorption in the daytime, and then E-layer absorption right along this area. So as the E-layer fades away, it's very active in the middle of the day, it fades away in the afternoon. It's not so much a reflecting area as it just absorbs signals that are passing through it. Okay, we talk about NVIS. This kind of shows how remember we talked about 20 meters in the daytime? This is showing over time. Remember, that's the terminator right there. It's showing over time how the critical frequency, or the MUF or NVIS, changes with day and night. You need a different set of antennas for nighttime NVIS than you do for daytime, especially in the winter.
Frank, we've got about 5 minutes.
Yep, I think we're almost done. So we could use the Aurora to work on the VHF bands, mostly. Has anybody ever worked Aurora? Oh, what does it sound?
On voice, the guy sounds like he's talking like water. On CW, the tone isn't sharp.
Raspy. That's why I get raspy.
Yeah.
So that is true ionospheric propagation.
Yes.
On the HF bands, it sounds like flutter. On the VHF bands, it turns a nice clean CW note into and then sometimes you can't understand.
The higher you go, you can't hear, right?
You can't, it's hard to work voice notes.
Yeah.
And I talk about backscatter. This is, the Aurora is in this area called the Auroral Oval. This is the night side, pushed down, and the day side back here. We talked about Auroral backscatter just now. It can go all the way up to 450 megahertz with a very intense Aurora. It's rare when it happens. So I think that's about as much as we've got time to do. I just want to mention one more thing. Reverse beacon network. Does anybody use that?
All day long.
It's fantastic. So here's what it is. I'm going to end with this. www.reversebeacon.net. What it does, it has over 100 receivers all over the world that send their data into this website. So just get on the air and call 2 CQs and send your call twice. So CQ, W3LPL, W3LPL.
CW only.
CW already. And then go to this website and take a look at what receivers heard. And then you can tell what kind of, without knowing anything about propagation, you can just look at what receivers and where in the world they heard you. You go on 80 meters in the daytime, all these receivers in Philadelphia and New York are going to hear you. Go on 10 meters and nobody's going to hear you.
Is that fully automated, or are there like actually people doing that?
Yeah, there's 10,000 people.
It's going to give you your signal strength, your CW speed, your frequency you want.
It's computer.
So they
we never imagined.
they actually.
No, literally, all you have to do is get on the air, CQ, W3LPL, W3LPL. That gives the computer a chance to make a few mistakes. Just 2 CQs, call time twice.
Okay.
And then look there and see who heard you. You don't have to know anything about propagation. Everything I told you is unnecessary.
So basically they did.
Okay, so that's it.
It's the easiest way to prove that.
Just the audio.
That's right, exactly.
That's how it is.
Exactly. You're actually sounding the ionosphere.
Right. I can tell how the band is. I started at 5 watts, fully CQ, and then increased to 100 watts. By the time I hit 500 watts, I mean, I'm getting hundreds of spots.
Yeah.
On the European.
So you're going anything like that scientist?
I love it. I'm on 3-4 hours a day,
Yeah.
20 minutes 17.
Well, you should try making QSOs with people instead If you want to learn more, I guess these slides will be available for people to look at on a website. But the best way to learn more, if you're really interested, is to look at some of these topics and plug it into Google. And then you can get all kinds of accurate information, you get all kinds of stuff that's really wrong.
Frank, before.
Okay, someone wants to see. Oh, okay. Let's, way up.
From the gas tank.
You guys can go ahead. You just want to do it.
We need you to go ahead.
No, you don't stand up there.
You want me to take that?
Maybe draw or something.
Now that you all know, there's a whole lot more to AM radio than calling CQ.
Pressure.
A lot of science involved, which makes it really
Pressure has
fun.
to be a certain thing, you got a certain amount. So,
And you got a 160 meter antennas available, because that's what we're all gonna
know
do.
that you're leaking.
Does a 100-foot tree come with the antenna?
Christmas tree.
Oh.
You know that your gas happens.
Frank has been gracious enough to invite us all to his picnic in the summer. You can also hear, as I have in the past, several of Frank's presentations at Dayton. He usually fills a 400 room, standing room only, plus the 400 seated people at Dayton for any of his presentations, which are always interesting in many different ways. He talks about the history of radio, what happened, 50 years ago, whatever. Somebody will raise their hand, as we did here, and say, well, what about, and down another street we go.
Down in the weeds we go.
But we really appreciate you coming, Frank. If you come up a moment. Fairlawn Radio Club is proud to present you with.
Hey, very nice. Thank you very much.
Yes. Where'd our photographer go?
Take a picture.
I just did.
Yeah? Okay. Oh,
No, I
you
did, I did.
You did? Okay, thanks, Jim. Okay, well, thanks again for coming. Thanks for everybody. Tomorrow and Sunday, we'll be operating the VHF contest and the North American QSO party at the club station, opening at 12 noon and working until 9 o'clock on either or contest both days. Oh, on Sunday, we don't open until, no, we have
I think it's 10 a.m.
10 a.m. on Sunday. Noon tomorrow and 10 a.m. on Sunday. And anybody is welcome to come, even if you're not a ham, you can come and get on the air with us, we'll teach you what to do. You can log for us, you can do all sorts of stuff, so stop by the club, and thanks again for coming.
Thank you. Thanks for coming.